Some more examples of exponential growth and decay modeling. We have a bacteria culture. It's modeled by the function P at T equals 200 e to the kt, where T is going to be the time in hours and P is the population of bacteria. It's known that after T equals 5 hours, the population is going to be 1,000. So we're going to do three things. We're going to use the information to find the growth constant K. We're going to find what the population is going to be after 450 minutes. And then finally, we're going to find when the population will be 1,500 bacteria. All right, so let's go ahead first of all and try. We know that the initial value is 200, and that's fine. But let's substitute. We have T at 5, or P at 5, excuse me, is going to be equal to 1,000. Okay, so after 5 hours, we get 1,000. And so we could substitute 1,000 back in for P of T and 5 back in for T. And so we're going to get 1,000 is going to be equal to 200 e to the kt, or k times 5. Now, you might remember in the last video, we could solve easily by dividing both sides by 200. So this is just an exponential equation. We divide by 200. And so we get 5 is going to be equal to e to the 5k. Remember, e's and ln's undo each other, so I'm going to take the natural log of both sides. So ln of 5 equals ln of e to the 5k. And that means that ln of 5 is going to be equal to 5k, or ln 5 over 5 equals k. All right, and let's go ahead and approximate that. All right, so that way we can approximate it. This is the exact value, but we might want to approximate it just to make sure. So let's just go in here, clear this all out, and we have ln 5 divided by 5. And that gives us 0.3219. All right, if I wanted to round to 4 decimal places. So I'll just go ahead and do that, 0.3219. All right. So that's all we have to do so far to be able to find the growth constant K. All right. So in our next part of the problem, we want to try to figure out what's the population after 450 minutes. So right now we have that our population function is going to be equal to 200 e to the kt, or 0.3219t. And a very common error that I see students making is that, okay, well, the time is now 450, all right? And they're going to try to find P of 450, but that's not correct, all right? Because if you recall, the original problem was in hours, okay? So the time is in hours. So what we're going to have to do is we're going to have to convert our minutes to hours, okay? So what we're going to do is we're going to take 450 divided by 60, since there are 60 minutes per hour. And in our calculators, we can go ahead and do that. So we just take 450 divided by 60, and that gives us 7.5. All right, so that's going to be the time that we use in this problem. All right, so now let's substitute 7.5 back into this function, and that's going to give us our time, or I'm sorry, our population. Okay, so that's going to be 200 e to the 0.3219 times 7.5. All right, and then let's just go ahead and throw that in our calculators, just because we can't do that one by hand too easily. So that's going to be 200 e raised to the 0.3219 times 7.5. Probably should use parentheses. And let me just make sure my growth constant is 0.3219. Yep, it is. Times 7.5. All right, and that gives us 2,236.22, I guess, 28. So 2236 would be our answer for this. Okay, because we're dealing with whole numbers, we can't have half of bacteria. So 2236. At any time, we want to round these down. Okay, so remember, even if you had like something like 0.99, you would round that down. Okay, because we can't assume that that's going to round up to a whole bacteria. The last part of this problem says find when the population will be 1,500. Okay, so for part C, what we're going to do is we're going to solve for T, and we're going to say 1,500 is going to be equal to our 200e to the 0.3219t. And now we're just going to solve this just like we've solved every one of our other exponential sorts of relationships. So I'm going to divide by 200. I'm going to divide by 200. All right. In our calculators, we have 1,500 divided by 200, and that's going to give us 7.5. All right. So this number 7.5 keeps coming up in this problem. 200s cancel out, or have e to the 0.3219t. We're going to take the natural log of both sides. All right. And then we know that ln's and e's undo each other. So now we have the natural log of 7.5 is equal to 0.3219t. And then finally, we just divide both sides by 0.3219. All right. So in our calculators, we're going to go ahead and do that. So we have natural log of 7.5 divided by 0.3219, and it gives us 6.26. Okay, and that would be in hours. Okay, so if we look back here, remember t is in hours, so that's going to be 6.26, and I'll just squeeze that in hours. All right. So lots of stuff that we can do with these types of problems where we have to try to find k and t and just go through and use our exponential equations. All right. Another example, and this one's going to be more of like the years of modeling. So we have an exponential model, a equals a sub naught e to the kt, describes the population, which is going to be a, of some country in millions t years after 2003. So the population in the year 2003 is known to be 204.4 million. And then the year 2005, the population is known to be 205.6 million. All right, so we're going to do two things. We're going to use the above information to find an exponential model that'll represent the population T years after 2003. And then we're going to try to figure out when, in what year, we're going to have 221 million people there. Okay, so T years after 2003. Well, right here, the year is 2003, so T equals 0 is 204.4. That's actually the initial value, okay? So when we're solving this, we know right away that A sub 0, because it's in the year that we start with, that's going to be 204.4. Now, we have year 2005. And so 2005 minus 2003 is 2. So when t is equal to 2, the population is 205.6. So what that means, P of 2 equals 205.6. Now that's going to help us to find our growth constant. Okay? So if we put all that information together and throw that back into this model, we're going to have 205.6 is going to be equal to 204.4 e to the 2k, or k times 2, right? Because t is going to be equal to 2 in 2005. Now, just like every other problem that we solved, we're going to divide both sides by 204.4. And I'm going to do everything at the end. And then what I'm also going to do is I'm going to take the natural log of both sides to get rid of the e. So ln of 205.6 divided by 204.4 is going to be equal to natural log of e to the 2k. All right, remember these are commutative, they're associative, you can move them backwards. So that's just going to be equal to 2k, and finally we can divide both sides by 2. All right, we probably want to get an approximation for k, so let's just shove this into our calculator and figure out what the growth constant is going to be. So we have the natural log of 205.2 divided by, and I forgot what the number is, so 205.6 and 204.4. 204.4, and then we're going to divide that by 2. All right, and that gives me 0.00293. All right, so if I'm rounding it off to 5 decimal places, so our k is going to be 0.00293. All right, so that's our K, and that gives us our model now. Okay, so our A is going to be equal to, remember we said that A sub 0, 204.4, so we're just plugging it back in here. That's going to be 204.4 e to the kt. So that's 0.00293 t. So this is our model. Okay, that answers part A. Now for part B, we want to try to figure out when the population will be 221 million. Okay, in what year? So we have to be careful with this one because when we get our answer, we're still going to have to do a little bit more with it. Okay, so for part B, we're just setting A equal to 221. And so we get 221 equals 204.4 e to the 0.00293t. Just like we've done several times already, divide by 204.4. We're going to take the natural log of both sides. So ln of 221 divided by 204.4 is going to be the natural log of e to the 0.00293 t. E's and ln's undo each other, right? And so the last thing we could do is just divide both sides by this 0.00293. All right, so to just solve for t. So we have ln of 221 divided by 204.4, and we're going to divide that by 0.00293. Now that's going to be equal to t. Now let's shove that in our calculators. So we have natural log of 221 divided by 204.4, and then we had 0.00293. All right, so this 26.649 or 65, if we were to round it off, that's our t. Okay, so 22 point, what was it, 65 equals t. Now we're not done because the question asks, in what year will the population be 221 million? All right, so what we're going to have to do is, remember, it says that t represents the number of years after 2003. All right, so we're going to have to add this to 2003. Okay, so 2003 plus 2265 is going to end up being 2025.65, but the year that we're looking for is 2025. Okay, so it'll be a little bit closer to the end of 2025. All right, so we're just going to get rid of that 0.65 because we're looking for in what year does it happen. Okay, so that's our exponential functions with respect to growth. Okay, so in our next videos, we still have to look at decay, and we're also going to take a look at logistic as well as Newton's law of cooling types of problems.